Hello. So we'll start today with a new chapter, which is on impulse and momentum. So we have already seen in the work and energy chapter that we can relate work of forces to change in kinetic energy. In this chapter, we'll see that impulse of forces acting on a particle is equal to the change in their linear momentum. So first, let us introduce what is the linear impulse and what is the linear momentum for a particle. Then we'll see together, we'll derive the principle of linear impulse and momentum. After this, we'll move to particular cases of conservation of linear momentum. And at the end of this chapter, we'll be able to know in which cases we can use, for example, work and energy, in which cases it's easier to go to impulse and momentum. And in all cases, you can or solve using chapter 14 or combination of 12 and 13. You always have several, more than one methods to solve with. But work and energy, as we have seen in the previous chapter, can simplify the solution. And the same will apply here in case of impulse and momentum. You can solve in an easier way some problems instead of doing several steps. So instead of solving, for example, with 3 equations, you can solve with 2 equations, for example. So you can save your time by using these principles. So to start with, we will introduce what is the impulse and what is the momentum. When we talk about linear momentum, the linear momentum, by definition, linear momentum is mass times velocity, okay? And it's a vector. So we can call it a vector. They call it in some books, vector L. Vector L stands for linear momentum, which is m times v. It's a vector, okay? And we'll see that the change of linear momentum is related to the linear impulse. What is the linear impulse? The impulse, by definition, is the action of a force over a certain period of time. If you remember, in case of work, what was the definition? Work is integral F dot ds. So you project your force on the direction of motion to compute the work. While for momentum, you integrate not with position, you integrate with time. So this is the definition of linear impulse. Linear impulse is integral from T1 to T2 of f dt. It will take into consideration the effect of a force, application of a certain force for a certain period of time. Larger your force, larger your linear impulse. Larger is the time of application, larger is the impulse. So sometimes, if you want, you can produce for the same impulse, you can, if you have a very large force, you can reduce the time of application, okay? So if you want to produce a certain impulse, or you increase the force and you reduce the time of application, or you reduce the force and you increase the time of application. So this is the linear impulse. Now, what is the relation between linear impulse and linear momentum? To know the relation between the two, you need to go back to the basics, which is the Newton law. The Newton law states that sum of forces is equal to mass times acceleration. And we know by definition that acceleration is derivative of velocity with respect to time. So sum of forces can be written as mass times dv over dt. And as you can see here, the two variables of interest are velocity and time. So if you take the time variable to the other side, you do like what we call separation of variables in mathematics, you end up with sum of f dt equals to summation of m dv. And if you want to integrate both sides, from this side, your variable is time, so you integrate with time. You have summation of integral from T1 to T2 of f dt equals to m times integral from V1 to V2 of dv. If you integrate dv, the integral of dv is v. So you get from this side mv2 minus mv1. equal to summation of integral from T1 to T2 of f dt. This is why we say that the summation of linear impulses acting on a particle is equal to the variation of the linear momentum. So it's mv at state 2 minus mv at state 1. And in case you have zero linear impulse, so if summation of linear impulse is 0, then you can apply what we call conservation of linear momentum. That we'll use in next slides. Okay? Any question on this? So now, as usual, the integration you needed if f is variable with time. So to evaluate the linear impulse, you need to integrate f with time. But in case f is constant, you can take it outside of the integral, and then the impulse will be f times delta t. So integral f dt is called the linear impulse, and it will measure the effect of a force during the time of its application. The impulse acts in the same direction as the force, so it's a vector. It will have the same direction of the force applied. Okay, so impulse vector is integral f vector dt. And the magnitude of impulse is a Newton second, because you are multiplying a force by time. So the unit of impulse is a Newton times second. If the force is expressed as a function of time, the impulse is determined by integration. And if the force is constant, you can simply say that the impulse is f delta t. And graphically, if you represent f with time, the impulse represents the area limited by the graph, between the graph and t-axis. So now, this is what we call the principle of linear impulse and momentum. It's stating that the initial linear momentum plus summation of linear impulses acting on the particle is equal to the final linear momentum. Or in other terms, if mv1 was here, summation of impulses is equal to variation in linear momentum. This is a vectorial equation. And you know that a vectorial equation can be decomposed analytically in 2D into equations and in 3D into 3 equations. So you can decompose it into x, y, and z. For example, along x, you have mvx1 plus summation of impulses of fx dt. So these are impulse in x direction equals to mvx at state 2. You can do the same for y and the same for z. Okay? Now, sometimes we do some graphical presentations that can help us to understand the problem. So we can say that we can represent the initial linear momentum vector. We call it initial momentum diagram. We represent the particle. And we put the initial vector mv1, initial linear momentum. Now, under the effect of the forces acting on the particle, you have what we call the impulse diagram. In the impulse diagram, we represent all impulses, so integral f dt of all forces acting, all external forces acting on the particle, equals to the final momentum diagram, which is mv2. We'll see that sometimes this graph can help us. When doing problem, we'll use the graph, and we'll see how it can help us to solve our problem. Let us do some problems to practice on the idea of principle of impulse and momentum. And you will see that we will solve simply by chapter 12 and 13. But also linear momentum can allow us to solve in a simpler way with a smaller number of steps. Okay? So let us consider the following problem. In this problem, we have a 100-kilogram stone that is originally at rest on a smooth horizontal surface. If a towing force of 200 Newton is acting at an angle of 45 degrees during 10 seconds, we want to determine the final velocity and the normal force which the surface exerts on the stone during the time interval. Now you can tell me no need for principle of impulse and momentum. It's right. We can use our previous knowledge. If we don't want to use impulse and momentum, what can we say? We need to consider the normal force, and we need to consider V final. In general, whenever we want to calculate velocity at the final state, it's good to calculate first acceleration and then to apply from chapter 12 relation between acceleration and time. So this is a first approach, okay? You can say first, I apply Newton law in y, along y, sum of y equals to 0. I don't forget to add the weight. And they said smooth surface, so no friction. So from sum of y equal to 0, I get plus n minus w plus 200 cosine 45 equals to 0. So this will allow me to calculate my normal reaction. I get my normal, okay? Second step, to get V final, I need first to solve for AX. So sum of x equals MAX. Along x direction, what do I have? I have plus 200 cosine 45 only, okay? Equals to M, which is 10 kilogram, times AX, if I consider G to be 10, okay? Oh, sorry, M is 100 kilogram, yes. So 100 times AX, I solve for AX, okay? For the weight, it's 100 times 10, which is G, so the weight is 1,000. Okay, so once I solve for AX, I say this is a constant acceleration because my forces are constant. So whenever I have constant acceleration, to solve for V, I can use that V final is AXT plus V0, and I am done. Okay. Now, we'll see together that if we use the principle of linear impulse and momentum, instead of doing it in two steps, instead of doing sum of forces in x equals 0, then using the velocity relation, we can solve for V final in one equation. So the advantage of using the principle of linear impulse and momentum is that with a lower number of steps, we can solve for our unknowns. So let us write the principle of linear impulse and momentum in x direction. In x direction, what can we write? As we said, the initial linear momentum, which is mvx1 plus integral from 0, t1 is 0 seconds, t2 is 10 seconds. So integral from 0 to 10 of fx dt. Here, if you want, no need to perform integration because your only force in x is constant. So you can take it directly outside of the integral. So now we'll apply the integration. It's 200 cosine 45, which is the force in x, dt, equals to mvx at state 2, which is V final that you are looking for, okay? So now, since we start from rest, Vx1 is 0. Since our force is constant, the integration will give us 200 times cosine 45 times delta t, which is 10. So 2000 cosine 45 equals to m times V final. So equal to 100 times V final. And we solved for our velocity. We are done. Okay, so instead of using two equations, we just did it with one equation. Now, concerning n, you can solve it from sum of y equals 0. But you can also solve it from impulse and momentum. How to do this? If you want to use the linear impulse and momentum in y, what do you have in y? in y, no motion. So if you apply the impulse and momentum principle, you get the following. You get mvy at state 1, which is 0. You cancel it out, 0. Plus integral from 0 to 10 of sum of y dt. What are your forces in y? You have plus the normal minus the weight plus 200 sine 45 dt equals to the final linear momentum. And since no motion in y, linear momentum in y is 0, so also equal to 0, because Vy final is also 0. So we go back to the same relation before, because to have integral of a function equal to 0, this function should be 0. And actually, this presents what? This presents sum of forces in y. So sum of forces in y should be 0. Okay? So if you apply the linear momentum in y, you end up with the same result, because it's equivalent to say sum of y equal to 0. And if you apply it in x, you save a step. Instead of calculating acceleration then velocity, you find directly velocity. Okay? Any question on this problem? So now you will see that we have solved the majority of these problems before in chapter 13. And now we'll repeat the solution using impulse and momentum, because impulse and momentum can give me a simpler way to solve for my unknowns. So blocks A and B have a mass of 3 kilogram and 5 kilogram respectively. If the system is released from rest, determine the velocity of block B in 6 seconds. If you remember here, when we used the chapter 13, we consider block A alone, and we wrote Newton law for A, we wrote Newton law for B, and we related motion of A and B to solve for acceleration. Once we solve for acceleration, we use the relation between acceleration and velocity to get the final velocity. In impulse and momentum, you will save the last step. You don't need, since you directly relate to your velocity, you don't need to get acceleration, then get velocity. Okay? So in this problem, if you want to solve using impulse and momentum, we can take block A first, okay? If I take block A first and I consider forces acting on it, what are the forces acting on it? I have the weight, WA, and I have the tension, TA. Okay, and since I consider my coordinate downward, I can solve for linear impulse and momentum in this coordinate system. So I can write plus MA times VA initial at state 1. But since it's starting from rest, so you can directly put that VA1 is 0. Plus, here, all your forces will be constant. Why? Because this system is driven because of the difference in weights. And weights are constant. So, of course, tensions also will be constant. So all your forces are constant. That's why you don't need to integrate. And you can say my forces are constant, since what is driving the motion is the difference between weight forces, which are constant. So no need to integrate. You say I take WA minus TA, which is sum of forces in the positive direction, which is downward. WA minus TA times delta T. Delta T is 6 seconds, so you can replace delta T by 6. So delta T is known. WA, weight of A is known. TA is unknown. We don't know the value of TA. Now, this is equal to MA times VA2 final. So times VA2 after 6 seconds. So VA2 final. Okay, in this equation, we have two unknowns, TA and VA2 final. So we need to come up with new relations. Let us move to block B. For block B, it's exactly the same relation, but I replace WA by WB. And I replace TA by TB. So my new equation will be also 0 because initially starting from rest, plus WB minus TB delta T equals to MB times VB2 final. هلا VB2 final is given here. They told us, okay, the final velocity of B, no, sorry, they told us to find the final velocity of B, so it's an unknown. But they gave us the time. They gave us the time needed to reach this step, which is 6 seconds, okay? So until now, what are our unknowns? We have TA, unknown. We have TB, unknown. And also we have VA2 final and VB2 final. So we have 4 unknowns, but until now we just wrote 2 equations. But of course, the 2 remaining equations are simple to know. What should we do? Whenever we have a pulley system, we need to relate motion of A to B. So I can relate VA2 final to VB2 final. And to relate TA and TB, I consider pulley D because pulley D is massless. So sum of forces on this pulley is 0. So first, if I start with this pulley, pulley D, and I take this system, okay, I draw the free body diagram of it. What do I have? I have TA from this side. And since I am cutting here at 2 locations, so I have TB and TB. Okay, and since it's a massless pulley, sum of forces in Y is equal to 0. So I have plus TA minus 2TB equals to 0. In this way, I related tension in the cables. So TA is equal to 2TB. So the relation is TA equals 2 times TB. This is equation number 3. I still need a fourth equation to close my system. The fourth equation is by relating velocity of A to velocity of B. So if I consider my system here, this is my pulley system. I take a datum. This is for SA for pulley D, which is because the center of D is attached to block A, so they move together. And I take a coordinate for block B, SB. So now if I follow my chord, I have constant here. This is a constant plus SA first time is a constant plus SA another time, 2SA until now, plus constant plus SB. So the equation is 2SA plus SB is equal to a constant. So if I derive, I get a relation between velocities. So 2VA plus VB is equal to 0. Okay. And therefore, I can relate velocity of A. So VA2 is minus VB2 final over 2. Okay. And now if I replace in my equation, in my system of equations, if I replace TA by 2TB and I replace VA2 final by minus VB2 final over 2, I end up with a system of 2 equations with 2 unknowns. So I can solve for my velocity of B at final state. Okay, so if you want, it's very similar to what we did before, but before we solved first for accelerations of A and B in chapter 13. And to get velocity, we said we relate acceleration to velocity. So by using linear impulse and momentum, you directly solve for the velocity instead of solving for acceleration, then solving for velocity. Any question on this problem?
Yes, I have a question here
Yes.
about the tension in the cable.
Yes.
It's the same cable. It should be the same tension.
Yes. Whenever you have the same cable, it's the same tension. So for this one, when you go through this cable, the tension is the same. This is why when you cut here, it's TB. And when you cut here, it's also TB.
Okay, dear.
Doctor,
Yes?
it has the same tension because it's the same length يعني ما بيمغط أو شيء أو ما خاص.
No, mahas. Because the pulley is massless. This is the reason. Pulley is massless and no friction acting on it. Frictionless pulley, so you don't have a net friction on the pulley. Okay? And because it's massless, if you do sum of moments about this point, you get zero. So since sum of moment about this point is zero, the force here should be equal to the force here. So whenever you have massless pulleys and frictionless pulleys, these two come, and if they don't mention anything, you can consider these assumptions. For massless and frictionless pulleys, the tension is the same over the cable.
Okay, doctor, thank you.
Welcome. Other question?
If there is friction in the pulley, T is not the same.
If there is a friction with the pulley, T is not the same, yes.
Okay.
Because then the friction, you have the friction force will do a moment about this point, and then these two forces moment will not cancel out, so they should not have to be equal. Okay.
بس دكتور إذا بدنا نستعمل relations لchapter 13 يعني نطلع acceleration بيرجع velocity
نعم.
velocity بنرجع بنطلعها من ال differential equation.
مظبوط. بس هون فيك بتقولي because A is constant, you can directly apply that V is AT plus V0.
Okay, thank you.
Okay, welcome. Now, what if we have several particles? If we have several particles, we can apply the principle of linear impulse and momentum for the system of particles. What will happen then? So you will consider summation of linear momentums at state 1. Now, you know, when you have a system of particles, the internal forces will cancel out by action-reaction. So you end up only with external forces. So plus summation of impulses, linear impulses of external forces from T1 to T2 equals to the final linear momentum. So since you have several particles here, you need to sum their linear momentums. So in case you are dealing with system of particles, you can apply the principle on the system. And this idea is very important when you have collision. Because what do I mean by collision? Let's say you have two particles and you know their initial velocities, they will collide with each other and then they will separate, okay? Whenever you have collision, dominant forces are forces of collision. Yani if you have an accident between two cars, during the accident, you have a very strong force acting between the two. So the impulse of this force will be dominant over all other external forces. So whenever we have a collision or shock, okay, you know that during an accident or during a collision, the time of collision is really limited. It's tending to zero. So dt will tend to zero. That's why the impulse will be important only if f is really high, okay? So whenever you have a problem of shock or collision between particles, you can say that the forces that will have considerable impulse are only the one related to the collision, yani, or the interaction force directly, or any force related to it. We'll see to after what do you mean by this. But all other forces, let's say the weight, the normal, etc., the forces that are not related to the collision force will have a negligible linear momentum, linear impulse. Why? Because dt is tending to 0 and the force is not very large, so you can neglect the linear impulse. And this is why you have an advantage whenever you have collision. You have an advantage of taking the whole system of the two particles, because in this way, when you take the whole system, the collision force will be internal, and by action reaction, the collision forces will cancel out. And you can say that all other forces, normal forces as weight, normal reactions, etc., which are not affected by collision forces, will have an impulse nearly zero. This is why during a collision, you can say, I neglect, when you take the system of particles, I neglect the external impulses, and I say I can apply conservation of linear momentum. So this idea is very used, conservation of linear momentum during collision is very used to find the final velocity after collision. So when the sum of external impulses acting on a system is zero, the equation will reduce to summation of linear momentum equal at initial state equal to summation of linear momentum at final state. And this is what we call conservation of linear momentum. Let us see how to apply this. We'll see how to apply this in problems. So keep in mind, internal impulses of the system will always cancel out as they occur in equal but opposite directions. So they will cancel each other. So the forces causing negligible impulses are called, and the forces causing negligible impulses are called non-impulsive forces. So whenever I have collision, the impulsive force or the interactive force between the two bodies in contact. But all other external forces like weight, normal, that are not related to the impulse force will become non-impulsive because the time of application is really small, okay? And the force is not very large, so the impulse is nearly zero. So this is what we mean by non-impulsive forces. We can neglect their impulse. So forces that are very large and act for a very short period of time are called impulsive forces. While if the time is short and forces are not very high, they are called non-impulsive forces. To understand how to use these concepts, let us start with a simple example. In this problem, we have two trains, if you want, that will do an accident with each other. So the 15 megagram boxcar A is costing at 1.5 meters per second on the horizontal track when it encounters a 12 megagram tank B costing at 0.75 meters per second towards it. If the cars meet and couple together, what do we understand by the cars will couple together? Who can tell me?
We're gonna have one FPT.
We want to have one final velocity. So they will become one rigid body, okay? So we can say that VA final equals to VB final. They will become one rigid body. You know, sometimes if you have a very strong accident, you have very high deformation of the cars due to accident, they will stick to each other. Then they will become as one object. So this is called the plastic collision. So you have complete deformation. You are not able to separate the cars. And the cars after the accident will not separate anymore. Of course, you need to put an external action to separate them. But under the effect of the accident, they will stick to each other and form one body. So this is what we mean by they couple together. Now, the question is to find the speed of the two cars just after coupling, okay? So we know the initial velocities of the two cars. We need to find the final velocity. This is why here it's interesting to take the whole system, A plus B, Because when we take A plus B as system, okay, the dominant force is the internal impulsive force. So you have F of A on B that will be opposed by F of B on A. So the impulses of these two forces will cancel out. And all other forces are non-impulsive. Yani what can be other forces? Other forces can be friction with the ground. Okay, you have friction with the ground. You have in X direction. In Y direction, you have weights and normal forces. All of these are non-impulsive because they are negligible compared to the impulsive force. Okay. So now you can say the following. You can say, since the accident is very fast and the dominant forces are the impulsive one, then neglecting, if we have friction, for example, here I didn't mention anything, but even if we have friction with the ground, it will be non-impulsive. So we can neglect its impulse. So now if you consider the whole system A plus B, and we write the impulse and momentum in X direction, what can we write? We can say summation of linear impulse. So MA VAX1 or VAX initial if you want, plus the linear impulse of B. So plus MB VBX initial. Since we have no external impulses, they are negligible, we can apply conservation of linear momentum. So it's equal to MAVA final plus MBVB final. But keep in mind that they have the same final velocities. Both cars will have same final velocity. So you can take final velocity into factor. So you get MA plus MB times V final. Okay. And in this equation, please keep in mind, you need to substitute velocities by algebraic values. This means that because I selected the positive direction to the right, VA, I replace it by plus 1.5, while VB, I replace it by minus 0.75 because it's moving in the negative direction. And for masses, I replace in kilogram. You can, if you want, you can keep masses in megagram because they will cancel out. And here, you use the same units for masses in both sides of your equation. So no need even to convert. So you can use here 15, here 12, and here's the summation 15 plus 12, 27. So unit of mass will cancel out, okay? And you did use that V final. You can find the expression of V final. V final is 15 times 1.5 minus 12 times 0.75 over 27 over the total mass of A plus B. This will give you the final velocity of your system. Okay? Now, in the second question, they want you to calculate the average force between the two cars if the accident take place in 0.8 seconds. Now to find the force between the two, we cannot take the whole system because when we take the whole system, these forces are internal. So now, or you take A as a system, or you take B as a system. Both will give you exactly the same result. Okay, let us do it. We can take A alone or B alone, and we'll apply on it the principle of linear impulse and momentum. Now, okay, yeah.